Hi everybody, this is Mr. Folly, and welcome to the wonderful world of Podcast 10.1. Can you believe we're through 10 units already? Quick review of intramolecular forces, and then telling you what types of intermolecular forces we have. Solubility actually comes a little bit lower than this, but that's alright. Organic functional groups, so we have to be able to identify them, and then comparison of intermolecular strength and length. So let's hop right into it. Conceptually, this one's pretty good. Intra means within. Bonds within molecules are much stronger than those between molecules. So my example is if there's this cliff and somebody is falling off the cliff, and then there's the typical movie thing, give me your hand. My arm's very close here. Give me your hand. Where is the bond going to fall apart? It's going to fall apart between the two people. It is not going to happen within one of us. It's not like whoever this person is with a red arm, oh, your shoulder's going to come unseparated. It's going to become separated, and then you're going to have poor little red guy falling down with just one arm, and you're left with poor little blue guy. Oops, he's not blue anymore. Poor little blue guy standing there with three arms because he's got the red guy's arm in his hand, just looking shocked and sad as he falls to his death. So remember, intra means within, so the bonds within a molecule are much, 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 much stronger. So if I'm talking about water, water looks like Mickey Mouse. The bonds between the ears of Mickey Mouse are unbelievably strong compared to the bonds between the Mickey Mouses. So this bond right here is much, 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 much weaker. All right. Ionic, here's the different types: ionic, covalent, metallic, and basically ionic is the strongest, covalent is the weakest, and metallic is really, I'm just going to say unpredictable. It ranges so much between it, so it has such a wide range, it overlaps both of them. Inter means between. An interstate runs between states. So there's always the bad email of Hawaii has interstates, like there's a road between, some Idaho and Hawaii. They're much weaker, but there are rankings. Ranked from weakest to strongest, van der Waals, which are also called London dispersion forces, are the weakest. Then dipole-dipole, then H-bond. This dipole-dipole, we learned how, this isn't really a comma thing, this should be a dash. Dipole-dipole means a polar molecule is attracted to another polar molecule. So this is a flat-out positive attracts negative. And we'll get into the nuances of the other ones. All of these occur to some sort of positive and negative attraction. Never gravity. It's always electron-ish. So, first look at van der Waals forces, also called London dispersion forces or just plain old dispersion forces. All things have electrons. More electrons means more chance for uneven distribution. So if I think of this giant atom with a little nucleus, and it has 100 electrons, is it possible, if it has 100 electrons, because electrons are moving around so crazy, to have 51 on one side and 49 on the other? Yep. If that happens, I've got a little negative over here, a little delta negative, and a little delta positive over here. Now if there's another atom next door to it, and there's a little delta positive over here, won't that attract its electrons? So this might even go so crazy to have 52, probably 40, 51, but you get the idea. And then there's a little bit of an attraction between them, just a little bit. And because it's just from random electron motion, the electrons will reposition themselves, and then it will be gone. So it's the quick little flirtation thing that lasts for just a second, but not much longer. And the more electrons you have, the more chance for uneven distribution. So a bigger number, just by pure probability of where they're going to be, won't be split up as much. All things have these forces, and these forces would be van der Waals or London dispersion forces. Don't forget to include them. Often AP says list all of the forces involved, and you must always include van der Waals or London dispersion forces. If they ask why one thing has a greater van der Waals force than another, you would say that it has a bigger mass, and bigger means more electrons, and you need to have the key phrase more polarizable. Remember, if you're polar, this right here would be polarized because you've got a positive pole and a negative pole. So more polarizable needs to be there. London dispersion forces and van der Waals are often called transient dipoles. So they're polar for a second, then they're not. Hopefully this picture will come through for you so you can see the steps that goes through it. This is in your book as well. We are in Chapter 10. Atom A and B. Notice we've got a perfect circle-ish. And then there's no polarization here. Then what happens is by chance, one end has a little bit more electron density than the other. So that makes it positive. So you start off with a delta negative and a delta positive, and then they shift to attract just like what I drew on the other side. So you get a temporary dipole. Dipole-dipole is a permanent dipole. That means it's made out of polar molecules. What about polar bonds? Nope, polar molecules. Okay, you need polar molecules. Remember, to be polar, you have two different elements bonded to each other. So remember, not the same equals polar, except C to H is always nonpolar. More change in electronegativity means it's more polar. And the more polar it is means it's got a more attractive end. So, you know, if you say two things that make someone attractive are their mind and their sense of humor, you know, if you've got a really good mind, then you can be funnier because you can have more different ways to be, and they both go in there. So this would be the positive. One side's more positive, the other side's going to be more negative, and you're more attractive on both ends. Extra oxygens increase polarity. So more polar means stronger acid. So it's this polarity that makes it stronger. HF is the exception to that. H2SO4 is a stronger acid than H2SO3. HNO3 is a stronger acid than HNO2 because where this polarity happens, there's a double bond somewhere in here. I don't even know where it is. But what happens is this oxygen helps pull electrons down here, which makes this bond even more polar. So if this is a very positive hydrogen, when water comes along with its two little hydrogens here, it's going to be very attracted to that lone pair. Okay. So more oxygens, a neighboring oxygen is going to make something more polar. Here's a picture of different attractions between polar and nonpolar things, these little oval things. Of course, the positive will be attracted to a negative. And if you've got a big glob of these things, then you can see how this positive can be attracted to two negatives at the same time, and this negative can be attracted to two positives. And it also reminds us that there's also repulsive forces occurring between the negatives that are around there too. So they tend to arrange themselves to be where they have the most attraction to the farthest ones. And remember, these things actually form itty-bitty weak bonds, and if you form a bond, you release energy, which makes you more stable and less of a shaken baby. Hydrogen bonds are the Corvette of dipole-dipole. What I mean by this is hydrogen bond is a dipole-dipole bond, but it's such a great dipole-dipole bond, it's in its own category. If you look in the newspaper to buy a car, you know, they have the different types of cars. They have, I don't know, Chrysler, Ford, GMC. And then under Chevy, there's Chevy. And then later on, there's Corvette. Now, a Corvette is a Chevy, but it's such a great Chevy that it has its own listing. It's that special. That's how special hydrogen bonds are. They're very electronegative, so they have extreme properties. A Corvette is a car, but it's not just a car. It's a Corvette. Ooh, yeah, balding men get them all the time so they can try and get younger wives. H-bonding means that an H is bonded directly to N or F. So, for example, ammonia is H-bonded because N is directly bonded to H, N, or F. But if I have whatever. If I have this set up right here, H is not directly bonded to F. None of them are. They're bonded to C. So that would be no. That's my not an example thing. Okay. Examples would be water, H-O-H. I did ammonia over here as another example. The only F example is HF because they both form just one bond. And that would be it. Water and alcohols are the most common example of hydrogen bonds that we'll see. This picture really emphasizes something on hydrogen bonds that it's not even drawn here, but the positive hydrogens are actually attracted, yes, to the negative end, but there's a lone pair right there. So a lone pair of electrons is a very high negative density right there, so the positive and negatives would form there. So NO and F, they have that strong intermolecular force, yes, because of the polarity, but also to some extent because it has that pair of electrons that goes through it. Organic for us is basically rank the polarities. And this is going to be very cheesy, but here we go. The most polar is carboxylic acids, which is going to be R, C, O, O, H. So looking at this, you see your hydrogen bond, and you've got this oxygen to make it even more polar. So that's the most polar thing that you have. And then we have alcohols, which has R just means anything. It doesn't really matter what it is. But you've got carbon bonded to O bonded to H, and that's what an alcohol looks like. And ester is R, C, O, O, R. So here you have just a polar part right here. The C to O is a polar bond. And then this oxygen doesn't help it a whole lot, but it's in there. Then you've got a ketone, which is R, C, R, and it's got a double bonded O here. And then an ether. Why am I forgetting what an ether is? Oh, it's an R, C, O, C, R. And those of you which would be Alex, who's taking chemistry, knows that I put too many C's in here, but it's not too many. It's just the way it is. And this would have a slight polarity, and this is barely it at all. Something with no O's and no N's means no polar, because all you would have left, all you would have left would be C and H. No polar. I got her up. Bell's going to ring in a second for me. I didn't explain the polarity rank, but don't name them yet. So we don't need to identify the functional groups. We just need to be able to say, this is better than this one is better than this one. Oxygen is so electronegative that it makes its neighbors electronegative. That's why Peter Molnar hangs out with Alex Molnar, because Peter is so darn attractive that it makes Alex look even better. So without that attractiveness, they'd be going someplace else. Oh, wait, they don't really hang out. I wonder which one's not attractive then. Long organic chains can have both polar and nonpolar parts. That's what soap is. Soap has a polar part and a nonpolar part. That way it can dissolve the nonpolar part, dirt, and dissolve that in the polar part, water, so that you can rinse away your filth and grime. Solubility, like dissolves like. Polar dissolves polar because they're attracted to each other. Nonpolar dissolves nonpolar more because of lack of repulsion than anything else. Polar won't dissolve a nonpolar because it's too attracted to itself. Polar things think they're so cool that they don't want to hang out with anybody who's not polar. So Mike Taylor would rather stay at home and play World of Warcraft because he's so cool hanging out by himself than hang out with you because you're not as cool as Mike by himself playing World of Warcraft. Water is called the universal solvent. That's a huge lie. It dissolves most anything polar, but most things are polar. What is more soluble in water, propanoic acid or propanone? Oic acid means it's a carboxylic acid. It would be more polar, and it would be C, 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 OH. And then fill in the H's, or C, 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 O. Fill in the H's. Comparison of intra-molecular bonds based on bond length. So P4, the molecule for phosphorus is P4, and this would mean the P to P to P to P. That's what P4 would look like. Those little bonds are 220. The bonds things between this and a neighboring one are 380. Remember, longer bonds are weaker. So basically all it means is the bigger the bond, the weaker the bond. Really? Even when comparing inter and intra? Yes, most definitely. So notice here, 200 versus 360, that's substantially weaker. To review, inter and intramolecular bonds are very different in strength and size. Biology is still dumb. Biology says hydrogen bonding is a strong bond. Hydrogen bonding is not a strong bond. Intermolecular bonds, like hydrogen bonding, are very, 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 very weak. Now, hydrogen bonding is the strongest intermolecular bond. But being the strongest intermolecular bond is like being the strongest second grader in the world. Ooh, yeah, in your face, dude. If you're the strongest second grader in the world, that means that Alana could still kick his butt. All right, so just to get the idea. Everything has London dispersion forces. Don't forget to include them. Know all your types of intermolecular forces. London dispersion forces, dipole, dipole, H bond. Identify them. And identify polarity rankings and give structural formulas for organic. Structural formulas just means identify it right now. All you have to do is identify it. That, and know that we're out of here in under 15 minutes. Have a good one.